On the 3rd of April 2021, me and the owner of another Polish debunking channel, Tomasz Midle, took a rented Theodolite and went to two places in Sopot, Poland, to Strzeleckie Hill, in Polish Wzniesienie Strzeleckie, and to Mount Glinna, in Polish Glinna Góra. We were going to perform an experiment. The idea is quite simple, to choose a few distant points on the shore so that all of them are at the sea level and measure zenith angles to them with the Theodolite. Knowing the distances to these points and the measured angles, one can calculate the vertical distance of the points from the local horizontal plane of the Theodolite. Now the most important part. This is enough to tell the shape of the surface of the water. If the water is horizontal, as flat earthers are saying, the vertical distances should be independent of the horizontal distance, with a caveat I'll cover in a moment. On the other hand, if the water surface forms a sphere, the vertical distance should grow with the horizontal distance. Let's talk about the caveat I mentioned, the atmospheric refraction which affects the results. We made the observations from roughly 82 meters and 109 meters above the sea level, quite far from the water, so the standard atmosphere will be a good approximation. Under these standard conditions, light rays in the atmosphere curve slightly downwards, in accordance with the laws of optics. The rays curve towards the denser medium, and the atmosphere is denser at lower altitudes and less dense at higher altitudes, at least usually. This should cause the measured vertical distances to be slightly lower than those implied by geometry alone. I'll show concrete values later, calculated with my own refraction calculator. So, where do we get distances to the points? We intended to measure them too by performing what is called a position intersection. Knowing the distance between two positions from which we observe a third point and the horizontal angles, one can calculate the distance to the observed point. Unfortunately, with the distances between observation positions available to us, which were 5 to 7 meters, the measurement of distances on the order of 30 kilometers were too uncertain, so we had to resort to using distances from maps. As I mentioned before, we were making observations from two places, a viewpoint on the Strzeleckie Hill and another viewpoint on Mount Glinna. At each of these places we measured vertical and horizontal angles to 4 different points. At Strzeleckie Hill we observed the following points. First, the Sopot pier, at a distance from the observation point of slightly less than 2 kilometers, as you can see in this screenshot from Google Earth. Second, a green post near the tip of the breakwater at the Gdańsk port, at a distance of about 8 kilometers. Third, a tip of another construction in the Gdańsk port, at a distance of about 11.5 kilometers, slightly more. And fourth, some point at the beach behind the Gdańsk port. We identified it by a distinctive tree or tower poking out of the tree line behind it. To find it on the map, I used its relative position to the crane here and the tower here that were a bit closer to us. And this method gives approximately this point at a distance of 23.3 kilometers from the observation point. From Mount Glinna we were sighting the following points. First, the Sopot pier again, this time at a distance of about 2.5 kilometers. Then the tip of the Hel Peninsula, and that's Hel with a single L, H-E-L, not double like the English word hell. And it was at a distance of slightly less than 25 kilometers. Then third, a point on the beach right below a distinctive bush. It was again a bit hard to find on the map, but satellite imagery did wonders here and I think I found it. And it would be at a distance of about 26 kilometers from the observation point. And finally, a point that I don't have a photo of, but it was a building with a tower which distinguished it quite much from other buildings on the shore, and it was at a distance of about 28 kilometers. We measured the angles to each of the points in two orientations of the scope. The second rotated 180 degrees relative to the first. This corresponds to measuring this angle in one orientation and this angle in the other one. The results should add up to 360 degrees, but usually they don't. This is because of various imprecisions in aiming the Theodolite and the construction of the Theodolite itself. In order to eliminate at least a part of the error, one can take the difference between the sum of the angles and 360 degrees to obtain the error and then subtract a half of it from the smaller of the two angles to get the corrected result. In addition, we measured each of the point twice from two slightly different positions because of the plans to measure the distance. I will be averaging the corrected vertical angles from both measurements and use values obtained this way for further analysis. For example, these are the results of the measurements of the Sopot pier from the Strzeleckie Hill. The sums of the angles, as you can see, differ slightly from 360 degrees. So we subtract 360 degrees to obtain the error, and we subtract half of it from the smaller angle. As the last step, we average the results. This will be the vertical angle we will use for this point. I entered the data from the measurements into a spreadsheet. The F column contains the angle in degrees as a decimal fraction. I will use the angle to the Sopot pier to determine the altitude above sea level of both observation positions in both the flat and the globe model. In order to do that, I used my own refraction calculator. I will put the link to the source code of the calculator on GitHub in the description. So basically what I did is I looked at the distance to the Sopot pier and the vertical angle. From the vertical angle I subtracted 90 degrees, so we're looking at an angle of 2.3958, and then I used trial and error to find an altitude that would reproduce this viewing angle with the assumption that the target is at an altitude of 0 and at a distance of this 1.955 here and 2.52 kilometers here. So, as you can see, these are the altitudes that do the trick. If you input them into the refraction calculator, you get the angles almost exactly. Here it gives 2.3959, it's slightly more than 2.3958, but it's the closest I could get with just two decimal places. And this is for flat Earth, you can see this flat here in the parameters. This is for globe Earth. It also reproduces almost exactly the angle with a slightly lower altitude. And these two are for Mount Glinna. As you can see here, it's 2.4795. And both of these give 2.4795 almost exactly. Now that I have the altitudes, I use them to generate the predictions for all the points in both models. Again, I used the refraction calculator to do that. You can see the commands I ran to generate the predicted angles and then to turn these angles into delta H in Python. So as you can see, I took the distances from here, the altitudes from here, and then I ran it in various combinations. So for the flat model I took this altitude and I ran 4 commands for different distances and I got these angles. And then for globe Earth I took this altitude, these distances again, and got these angles. These are the predicted angles from the models and with standard refraction. Then I took these angles and I converted them to delta H in Python, so here are the numbers. And now I'll take the numbers, fill in the columns here, and then using exactly the same procedure, I'll fill the predictions for the other viewpoint. With the predictions filled in, we are ready to enter the formulas calculating the delta H implied by the measurements. So here we take the distance from column B and multiply it by the tangent of the angle in radians. And the angle is the vertical angle from column F, and we subtract 90 from it. Okay, and that's it. So that's the measured delta H, and now we just copy this formula here, and we also copy it here. Okay, so we can see that the measured delta H increases with distance, in almost perfect accordance with the predictions for the globe. The differences can be easily explained by imprecise measurements and slight deviations of refraction on that day from standard refraction. On the other hand, if we look at the flat Earth predictions, they don't fit the measured values at all. Even if we disregard refraction and just assume constant delta H, so we would assume constantly 81.8 for example here and constantly 109.1 or something, this is still nowhere near the measured values. And the differences from the flat Earth model are definitely too much to be explained by measurement error or non-standard refraction. So to sum up, while it's true that the water looks flat to the naked eye, if we don't use the naked eye but a more sophisticated instrument like the Theodolite, the truth emerges plain as day. The water surface is curved and it drops with a distance from the observer, like this. So flat Earth doesn't match the results and globe Earth does. So thank you for your attention and see you the next time. Bye.